All right, so let's talk about what else we can do with differential equations, okay? So a large part of what you're going to be required to do with these is to take a differential equation and basically kind of undo the derivative aspect of it and figure out what the original equation would have been. So you're starting with a derivative essentially, and you're working backwards to finding what y would have equaled in the first place. Um, Again, like remember, we're just doing the most simplistic cases here, so we're not going to get anything real crazy. Meaning all of the differential equations that we will be solving are going to be of the first order, meaning first derivatives only, and they will all be separable. And so separable means that you can split your differential equation and put all of the y components on one side and all of the x components on the other side. So I'll show you what I mean. This one on the left here is a separable differential equation. I am able to essentially cross multiply, and when I do that, I would have y squared dy on one side and x squared dx on the other. And this is called separable because I've got all my y components on the left and all of my x components on the right. The second example is not separable. I would not be able to cross multiply because I have this +1 thing tacked on. So I'm not able to put all of the x terms on one side and all of the y terms on the other side in this case. And we won't really be dealing with solving non-separable differential equations, okay? For those of you that like steps, here is a step-by-step process of how to solve a differential equation. I love steps, but I'd rather show you an example of what to do. So you can refer back to this later, but I'm going to go skip forward and show you the process. So there's actually two questions on this slide. So the first one is find the general solution of the differential equation y prime equals x over y quantity squared. The first thing I'm going to do is I'm going to rewrite y prime as dy dx. And then I'm going to put my x over y quantity squared. Okay, that is step 0, I think it's called in the list, the order of things. And then the next thing you're going to do is do some algebra, which is not always needed. In this case, I do need to do some algebra. Essentially, I need to distribute the squared so that I don't have a component of everything in parentheses. I'd like everything to be kind of its own deal. So I'm just going to say that this would be the same as x squared over y squared. So separating the x and the y from one another. And then I'm able to use some algebra to like manipulate that. All right, so now we're going to separate. And separating means I'm putting all the y terms on one side and all the x terms on the other. I would say like 95% of the time that involves cross multiplication. There are some cases where it doesn't have that step, and hopefully I can show you an example of that here in a minute. So I'm going to multiply y squared over, and I'm going to multiply dx over. And so I would get something that looks like this. Y squared dy equals x squared dx. Okay, now here's the cool part. If I want to solve an equation for y and dy is beside it, that's kind of like a derivative, right? And so we've been learning actually how to undo a derivative. It's called an antiderivative. So what I'm going to do is I'm going to put an antiderivative symbol, but I have to do it on both sides because this is an equation and I do have to keep it balanced. So what I do to one side, I have to do to the other. And I'm going to antiderive both sides. Okay, remember dy is like the argument in the antiderivative that tells it how to operate. So this is y squared dy, which means I'm going to take the antiderivative with respect to y, and my equation has y's, so perfect, I can do that. So I would take the antiderivative, that would be 1/3 y to the third, And remember, this one doesn't have any integration values like a or a B value. So you would have to put plus C at the end. Let me make a little bit more room here. Okay, same thing on the other side. I have dx telling the antiderivative what to take the antiderivative with respect to, and it's with respect to x, and I have x's, so I'm able to do that. So I would have 1/3 x to the third, and I would also need a plus c. This is a little weird because I can't have c over here and c over there. They're two different values. Because one is for this side and the other is for the other side. So I need to make sure that I know that they're different. Usually I just put like a little subscript on it to denote that they are different values. Okay, next step is I'm going to solve for y. Remember, that's kind of the whole point of this. Okay, the whole point of this is to get y alone, find out what that original equation was. And so I need to solve for y. So I don't have a lot of work to do. I do need to do something with this C1, and I'm going to subtract it. So it's kind of like C1 is a constant, right? So is this. This is also a constant. So I'm just going to go over here and I'm going to make a note that C2 minus C1 just means some constant value minus some other constant value. I don't know what they are exactly, but I know that the result is also going to be a constant value. So then rather than writing C2 minus C1, I can just pick another letter that I want to represent whatever that constant difference would be. And so I'm going to choose to change it to D. This is not necessary every time. I'm trying to be proper with my math, and so technically that's what's happening. All right, next step. I'm going to multiply everything by 3 to get rid of this fraction. So I'm going to multiply the entire equation by 3. That would give me y to the third equals x to the third. Technically it would be 3 times d, but then there's that thing again, like 3 times d, what does that even mean? It just means another constant value. So you might as well just call it d. Just keep the letter the same. I don't even know if it was necessary for me to change this to d in the first place. It's just a constant. Okay, still constant value. And then last step is going to be I need to solve for y, so I need to undo the cubed by taking the cube root. So my answer would look like the cube root, I need the little 3, cube root of x to the third plus some constant value. Okay? I want to point out one thing. Because I don't know the value of the constant, this is called a general solution. A general solution to the differential because I don't know the value of d necessarily. All right, give me a moment. I want to make another slide. I don't like how I'm running out of room here. Okay, so we have to do part B. So part B says find the particular solution satisfying the initial condition y of 0 equals 2. So I'm going to pull my answer back from what we just did. We just found that the cube root of x to the third plus d was the general solution. Okay, and so we are going to use that value or that equation to help us find the particular solution. So this thing here is an initial condition, and what it means is it means that when x is 0, y is 2. That's like an ordered pair that exists on the original curve, 0, 2. And so in order to make it exist on the original curve, I need to plug those values in for x and for y. So 2 would be my x, and then 0 is my y value. And then I'm going to use them to figure out d. Or it used to be c, but you know, the constant. So essentially, we're going to do the math. In order to find d, I need to undo the cube root. So I would need to cube both sides. That would give me 8 equals 0 plus d, 0 to the third is 0, which means that the value of d is equal to 8. If I wanted the curve to go through the point 0, 2, the value would have to be 8 for d. And so the particular solution is going to be y equals, so I'm going to go back and write that equation I had before, but instead of d, I'm going to put 8. Okay, and then this is called your particular solution. Okay. All right, so I just want to do a couple more examples with the solving part. So this time we're not going to be finding the particular solution because I don't have an initial condition. So we're just going to work on the solving part. Step 0 in the solving process says to change any of your y primes, change them to dy dx, but we don't have to do that here because it was done for us. So then step 2 is separate. So I want all the y things on one side and all the x things on the other. So I'm going to take this entire denominator and I'm going to multiply it over. And then the same thing with dx, I'm going to multiply it over. I'm going to just be careful because my denominator does have it's a binomial, and so I want to make sure I keep it in parentheses to keep everything together. And so I think this is what it would look like if I kind of cross multiply this time. Everybody agree with that so far? Okay, so then step 2, I think maybe it says, is we're going to integrate. And again, we're integrating because we're trying to eliminate components of this equation, being dy and dx specifically right now. And remember that those are derivatives, and the only way to undo a derivative is to take the antiderivative. Okay, so I want to antiderive 2y. So remember that would be add 1 to your power, divide by that power. I can clean that up here in a moment as well. Antiderivative of cos y would be sine y plus c. And then over here, let's see, antiderivative 6x to the third divided by 3 plus c, and you can call it c1, c2 if you want. I think I'm gonna do a little bit differently this time. Let me clean it up. So this would be y squared plus sine y plus c equals 2x to the third plus c. And really kind of saying plus c on each side is rather silly because it just means there's a constant somewhere in the problem. So there's really no need to put the subtract c like I did last time because it's just going to make a constant. So what I would like to do is I'm trying to solve for y, so I'm just going to put all the extra stuff on the right side. And hold on one second, I don't like the way that looks. I'm just going to say subtracting c, kind of moving it over to the right side so that I have all the y components on one side of the equation. I'll just say, you know, it's some constant. I don't know what it is, but it's something. And then this one is interesting. There's a y in 2 spots. There's no way to take the y out of the sign, like with factoring or something, to solve here. So you're actually done. And I don't like when this happens because I really like to solve things completely. But it's not possible here. So this would be your answer. You can't get y alone. This is the best you can do. Okay, so same thing again. Let's just keep, this one's a little bit different with the setup. Solve the equation. So we're solving by finding the value of y. And the first thing I'm going to do is change y prime to dy dx. Here's why this one's different. When I go to do my separating step, I don't have a fraction on the right side like I have in every other example. So we're going to have to do something different. Pause and go to the next video.